I will get started. Let me begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for this class and these students. Just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So today is arguably the most important day in the whole course. So it would be like the worst possible day to miss. You know, just make up some kind of made-up reason to miss class. I mean, I don't know, but today we're talking about complex differentiability. Okay, so the complex derivative. All right, the complex derivative is really what we're talking about. The complex derivative, and so I think I told at least one, possibly two of you that the definition wasn't what I stated last time in this course. In fact, maybe I stated it last class. That is false. The definition is what I said last time. It's just not my preferred definition. So here it is. Let f be function on the complex numbers and z naught in the domain of f, all right? Then f prime of z naught is equal to the limit as z goes to z naught of f of z minus f of z naught divided by z minus z naught, right? You should really recognize this definition from Calculus 1. It's the difference quotient, right? And so if that's the case, we say f is complex differentiable at z naught if f prime of z naught exists, right? And by that I mean that the limit of that difference quotient exists, all right? And furthermore, I'm just going to throw this out here. If f prime of z exists for some epsilon, if f prime exists for, sorry, I dug myself a hole here. If there exists epsilon greater than 0, such that f prime of z exists for each z in the disk of radius epsilon centered at z naught, all right, then f is holomorphic at z naught, and we write f is an element of funny looking O of z naught. All right, this is what I mean by that is that the function is complex differentiable not just at the point, but also in points nearby the point. It's possible for a complex function to be complex differentiable at a point, but yet not holomorphic. All right. Likewise, if f is, holomorphic at each point in D, then f is an element of the holomorphic functions on D. And finally, let me finish this litany of information. We say f is entire if f is holomorphic on the whole complex plane. All right. So today I'm going to describe to you guys 4 seemingly different ways to describe the complex derivative. So the first of all, I already have on the board. All right, this is the so-called, difference quotient, limit of the difference quotient, right? So let's look at an example, real easy. Example 1, let's let f of z equal to z. What is f prime of z naught? So by properties of the limit, right, limit laws, they still hold here. We've got 1, which is 1. So I guess I should fess up, there's some notation here. What do we write in this instance? Just like we wrote in Calculus 1. We write d dz of z equals to 1. Or if you like, just dz dz is 1, right? Example 2. F of z equal to z conjugate. Then if we look at the limit as z goes to z naught of z bar minus z bar naught over z minus z naught, this does not exist. By last class, we proved this. We looked at two paths. And we found that that limit didn't exist by looking at the horizontal and the vertical path at an arbitrary point z naught. So what this means is that, f prime of z does not exist at all z, right? In other words, the complex conjugate function, like z bar, z maps to z bar, is nowhere complex differentiable. All right? And of course we could do fancier examples here. I'll do one for the sake of nostalgia. Let's see here. Example 3. Let's look at f of z equal to 1 over 3z plus 1. Let's do this one for old time's sake. Calculate f prime of z. How do you do that? Actually, let me introduce yet another way to do this. Let's calculate f prime of z. Let's calculate the limit in a different way. We could also calculate it as the limit as h goes to 0 of f of z plus h minus f of z. If you prefer to take this notation, you could also take this notation, right? Basically make a z minus z naught equals to h substitution in the previous limiting formulation. Right, we can trade a limit for z goes to z naught for a limit as z minus z naught, which is equal to h, goes to 0, if we do so choose, and I do at the moment, in order to add greater diversity to this lecture. All right, so anyway, yeah. So how's that go? Well, we can do the algebra, right? It's just algebra. So I like to write the 1 over h up front, and then I've got 1 over thrice z plus h plus 1 minus 1 over 3z plus 1. Make yourself one of them their common denominators. We got 1 over h. We got ourselves 3z plus 1 minus parentheses 3z plus 3h plus 1, close parentheses. Then we got 3 times z plus h plus 1. I'm not multiplying it out in the denominator. I just multiplied it out in the numerator. As you can see, some stuff cancels, right? There is some cancellation that goes on there. Like my 3z plus 1 cancels with that and that, and just leaves me this term, right? But then if you look at it, this h and that h, they're going to reduce and just leave you with the limit as h goes to 0 of minus 3 over 3 times z plus h plus 1, 3z plus 1, which now we can just plug it in, right? We get what? Minus 3 over 3z plus 1 squared. And there you go. And of course what this means in our usual notation is that ddz of 1 over 3z plus 1 is minus 3 over z plus 3z plus 1 squared, right? Totally unsurprising. This is what you would expect if complex differentiation works like real differentiation, right? And it does. All right, so there's that. Now, what else can I tell you here? So in the notes, I also look at, in the notes, if you look at example 5.1.5, I show that if you look at f of z equal to like z bar squared, excuse me, modulus of z squared, I show that that one also does not have a complex derivative, all right, at any point except possibly the origin when you look at it. So anyway, enough about that. In fact, this is not my preferred viewpoint. All right, so let's move on. What's the next viewpoint? The next viewpoint is the caratheodory. It's a mouthful, isn't it? Caratheodory definition. And so basically the central point of Caratheodory's theorem is if we look at, and so we're going to be thinking about basically z naught equals to a in this subsection. So if I was a better editor, I would have changed all of my z naughts to a in the last section, or I'd have changed all the a's to z naughts in this section, but hopefully you guys can adjust, right? If it helps you, change all of my a's to z naught right now to make it look like the last one. But we're thinking about this point and how to characterize f prime of a, okay? And so the central observation of Caratheodory's method is that you can write f of z minus f of a as equal to brackets f of z minus f of a over z minus a times z minus a, right? For what? For z not equal to a, right? So all I did was, divide and multiply by z minus a, right? Which is allowed if z is not equal to a. And if f is differentiable, what happens? If f is differentiable, then this difference quotient goes to the derivative, right? So maybe it's a good idea to give that thing a name. We call it the difference quotient function. And that brings us to Caratheodory's theorem. Let me write it down here. So here's the theorem. 5.2.1. Let f be a function on the complex numbers with a an element of the domain of f, a limit point. What's that mean, that a is a limit point? That, yeah, well, it means we can take a limit at the point, basically. So it means that the domain is defined near that on some open disk or something like that. There's infinitely many points for the function defined near that. Anyway, a careful definition of limit point was given in the notes earlier, so let's you look back at that if uncertain. But anyway, so complex, all right, then that's the end of that sentence. Then f is complex differentiable at z equals to a, if and only if there exists function phi from the domain of f to the complexes with the following two properties. What are the two properties? Number one, phi continuous at A. And two, f of z minus f of a is equal to phi of z times z minus a for z in the domain of f, okay? We say that a function phi with the properties as above is a difference quotient function of f at a. So, all right. So that's the theorem. So it's claiming that finding a function like this with these two properties is equivalent to the existence of the difference quotient's limit at that point. In other words, this is another way of characterizing complex differentiability. All right? So the proof of this theorem is not especially interesting, but I'll go through it just to try to make sure we understand each other. Although arguably my time might be better spent on like one more example about this stuff. I don't know. I'm going to go through the proof. I haven't talked myself out of it yet. So here we go. So we'll go this way. So what does that mean? We're assuming that it's complex differentiable. That f prime of z naught, I'm back to z naught again. F prime of a equals to the limit as z goes to a of f of z minus f of a over z minus a, right? Exists, yeah? So in the notes I say, suppose f is differentiable at a. To be more picky, I really should say it's complex differentiable at a. All right? So we're going to, so now our job is to construct this difference quotient function, right? So here's how we do it. We define phi of a equal to f prime of a, step one. Then, for z not equal to a, let phi of z equal to, well, f of z minus f of a over z minus a. Then what can you tell me about this function I just defined? First of all, is that reasonable? Can I do that for, for z not equal to a? I think I can, right? Because I don't have a division by 0. All right, so, all right. So let's see here.
Why don't you have a limit there?
Because I don't want one. It's not there. And then, let's see, does this phi satisfy the desired properties? Is it continuous at a, first of all? Does it give us number one? What does it take for phi to be continuous a? Note, how do we judge continuity, right? What's the limit as z goes to a of phi of z equal to? It's equal to the limit as z goes to a of f of z minus f of a over z minus a, right? But we know this, we're given that this exists, right? This is equal to what? This is equal to f prime of a, right? Which is by definition phi of a. Therefore, phi continuous at z equals to a, right? So number one, we check property number one, right? What's the property number two? Well, number two, if z is not equal to a, then notice that f of z minus f of a by construction is equal to phi of z times z minus a, right? What remains to check? That works for every a in the domain, excuse me, for every z in the domain except for a, right? So what do I have to check? What's left to check? Is equation true if I put z equals to a? How about this? If z is equal to a, then if we look at f of z minus f of a, we get what? we get f of a minus f of a, which is also known as 0. And is that equal to phi of a times a minus a, which is equal to f prime of a times 0? It is. Therefore, property 2 holds. But there is no limit in the phi. We don't have a limit in the phi. It is just the difference quotient function. It's not the limit of the difference quotient function. It's subtle, but this is the genius of caratheodory. Like you want to put that limit there, don't you? Yeah, but it's not there. And it helps us a lot. Now the other direction, we assume that, phi exists with 1 and 2, right? And thus, f prime of a is equal to what? The limit as z goes to a of f of z minus f of a over z minus a, which, by the way, by construction, is the limit as z goes to a of phi of z times z minus a over z minus a, right? Using property 2 for phi, right? By property 2. But then these two things be canceling, and you just got what? Phi of a by 1, right? So this one here is by 2. Therefore what? Thus, f prime of a is simply equal to phi of a. Now, you got to understand, guys, when I make an argument like this, some people who are more pedantic than me would object to my language, like that I've written f prime of a here, saying maybe I've assumed the point. But when I write something like this, I'm saying, I'm investigating whether f prime of a exists, right? So I allow myself sometimes to write f prime of a, to calculate a limit, to find that the limit doesn't exist, and then I will circle back and say, okay, so f prime of a doesn't exist, right? Some people who are more fussy than me won't even write f prime of a in this instance. But I'm not that person. Although I was that person over in example 2. If you study it carefully, you'll notice that I did not write f prime of z naught here because I was doing that thing over there. But I don't want to put that on you. There we go. This is the theorem of caratheodory. It is another way of characterizing complex differentiability. And it is incredibly useful as a method because it allows you to derive theorems in just a much more natural way. Like we teach you guys ways of calculating various limits, various theorems in calculus 1. And we show you proofs of those theorems which are involved in various kinds of sneaky addition of zeros and things like that. With the theorem of caratheodory, there is a straightforward, simple procedure for actually calculating, like product rule, for instance. Let me show you. So assume f and g are differentiable at a, complex differentiable, right? let f prime of a and g prime of a exist. Then we have two things. On the one hand, we can say that f of z is equal to f of a plus, let's call it phi sub f of z times z minus a. We can also say that g of z is equal to g of a plus phi sub g of z times z minus a by caratheodory. All right, this is the method of caratheodory. It wraps up all of the past constant terms in this difference quotient function. It's not quite the linearization, because the coefficient of z minus a is not a constant, like it would be if we put the limit there. You see, that's the difference. Not putting a limit there makes the difference quotient, the quotient, the thing that multiplies the linear term, not a constant, but a function, which means it's not an approximation. It's an exact statement that nevertheless ties into the linearization approximation through the limit. So then you want to find what's the derivative of f times g. So you multiply f of z times g of z. What happens? We got ourselves f of a plus phi sub f times z minus a, big parentheses, times g of z, g of a plus phi sub g of z times z minus a, right? You guys know how to multiply, right? So we multiply. You got yourself f of a times g of a plus, and I'm going to be a little cagey here and do a little math. We got ourselves an f of a times phi g of z plus phi sub f of z times g of a plus phi sub f of z, phi sub g of z times z minus a. Close my big parentheses. I factored out a z minus a. You're like, why did you do that? Well, this isn't the first time I've done this calculation, so I know where I'm going. You know, okay, fine. You guys are not used to this method, so this is something you'd have to learn to do this, right? Fine, but once I do that, this is just algebra, right? 2 things times 2 things gives you 4 things. 1, 2, 3, 4. 4 things. Right? So the question is, can we identify the difference quotient function for the product? What's the difference quotient function for the product? I argue that this animal right here is my difference quotient function for the product. It's literally phi f g of z. Now, does that work? Is that a continuous function? All right. So, in your homework, oh wait a minute, no, I don't. Do I need your homework yet? Oh, I don't. We don't have to think about continuity everywhere. We think about continuity at A. Is this continuous at A? Well, f of A is a constant, no issue there. Phi g is given to be continuous at A. Phi f is given to be continuous at A. Continuous at A. We have the sum and product of continuous functions at A, which is once more continuous at A. So it's continuous at A. We got property number 1. Property number 2 is by design. I have done this calculation, so it is the case that f of z, g of z, minus f of a, g of a, all divided by z minus a is equal to what? It's equal to phi f g of z, right? Or if you like, I could put the z minus a over there like I wrote in number 2. You know? Like I put the z minus a multiplicatively over here, I just divide it over there. If you like me to make it number 2 exactly, I just move this over here. Yeah? There you go. Little crooked, but item number 2. Yes, sir.
So are you claiming that if you have a phi that satisfies those properties, then it's the derivative?
We just proved that, yes.
Okay.
Yeah. We proved that having a complex function that has a difference quotient function with those 2 properties is equivalent to the existence of the derivative of that function at that point.
But like, so if we have one, then the derivative exists, but it also has to be phi.
Well, if the derivative exists, it's unique, so there's no issue. Like, if there's something that's the derivative, it is the derivative. It's not a derivative.
Okay.
So maybe that's a hole we should fill. Homework problem. Show the derivatives exist. If it exists, is unique, you know? Did I put that in the homework? I don't think I did. Where else could I put that? If I used my homework, I used my quiz. Where could I have people prove the derivative's unique? If not in the homework or quiz or mission. Huh. Something to think about. But anyway, so this satisfies the two properties, right? Therefore, the derivative of the product, what this proves is that if you have two complex differentiable functions, the product of those functions is again complex differentiable. And what's the derivative? Well, we just take the limit of this thing, right? Another part of, like a corollary, or perhaps part of the theorem I should state, is that if this difference quotient function exists, the value of the difference quotient at A is the derivative of the function at A. That's part of this proof if you look at it, right? See that? The value of the difference quotient at A is f prime of A. So thus, fg prime of A is equal to the limit of this, right? And don't make me write all the steps out here, but you guys tell me how it works out. Like, look at it. Tell me what the answer is. What happens with this first term? As z goes to A, this goes to what? F of A times what?
Bg of A.
No. Well, yeah, but what is that?
What's f prime of A? Or g prime of A.
There you go. So that would be g prime of A. And then plus what? So we did that piece, right?
Plus f prime g.
Plus f prime of A. Yeah? Times what? That's this piece. That limits to that. And then g of A is g of A. What about that other term in the difference quotient function?
0.
Right, this goes to 0 because it's f prime of A, g prime of A times a 0. There you go. What is this? That is the product rule. I didn't add 0. I didn't do any kind of funny business. I didn't even need to assume the continuity of the function on the basis of the differentiability like you do in the usual proof in Calculus 1. This is always a better proof than we give you in Calculus 1. And I would point out that in the differential operator notation, it looks like this. d dz of f times g is equal to df dz times g plus f times dg dz, right? Ye old product rule. Hooray, still true for complex derivatives. Now, we could do more in this formalism, right? Certainly, we could go on and we could prove the quotient rule by finding the difference quotient for the quotient of two complex functions. That is in my notes. I refuse to present that in class as it is most horrible. But if you look, I mean, it is. So if you're ever teaching Calculus 1 and you want to make your life easier, skip the proof of the quotient rule. It is nasty. Just saying. Nasty, nasty. Quite nasty. But if you look at page 54 in my notes, I think, I do have a proof that like the quotient rule also goes through for complex valued functions. And we also have a sum rule, and you can pull constants out, and there's even a chain rule, right? So all of your usual rules of calculus all transfer through to complex differentiation. So the good news is, if you know how to differentiate in Calculus 1, and you can change an x to a z, well, you're good to go for the most part in here. It's kind of anticlimactic, right? Given all the you know, subtlety we found with the logarithm and the principal square roots and that stuff. Like that was pretty subtle, wasn't it? But this is really just calculus 1 all over again. Really, this part of it. So I guess I should at least write those out. I think you guys know these without me writing them, but for the sake of completeness, let me say, we do know that ddz of f plus g is df dz plus dg dz. What's the presumption of this theorem?
Derivatives are linear?
The derivatives are linear. No. How about just the derivatives exist? So this last one is the chain rule, right? If I wrote this in terms of the prime notation, it looks like this: f prime at g of z. Excuse me, my bad. It's the composite rule, right? So f composed with g prime of z is equal to f prime evaluated at g of z times g prime of z. That's how the chain rule looks in the prime notation. But this is like a slick notation, right? It says differentiate the outside function and evaluate it at the inside function, which I'm calling w, and then differentiate the inside function with respect to z, multiply it. That's the chain rule. Now I do have the proof of the chain rule in the homework, and I want you guys to try to prove that rule using the theorem of caratheodory. All right. So, and I have a note here in my notes which says see section 4.9 of calculus. That's how you say that. It's calculus with an exclamation point. So in there I have a proof of the chain rule for real calculus. It can literally be copied, changing x's to z's, and probably be correct if you think about it. So, all right. So I go on here in the notes to do derivatives for a bunch of functions by the theorem of caratheodory, all right? So I'll do like one of these. I'll let you read the other ones. I don't want to do too many. I'll do one that's relatively nice. I'll do the square function. What example am I on? 4? So this is the fourth one? All right, example 4. So let's look at f of z equal to z squared. And so then, all right, let's look at this. We've got f of z minus f of a is what? Z squared minus a squared, right? So factor that thing. You got yourself z plus a times z minus a. So what's my caratheodory function, if you like, or my difference quotient function? What's my phi? Right here. See this? This is what I should take to be phi of z. Does it work? Is that continuous at a? It certainly is, right? Does it satisfy item number 2 that I just erased? Yes, by construction. It satisfies f of z minus f of a is the difference quotient function times z minus a. So it satisfies the 2 criterias. Therefore, the derivative of f of z equals z squared exists. And what is the derivative? It is the limit as z goes to a of z plus a, which is, I think it's 2a, right? There you go. And so, of course, if we go back to the differential notation, we have ddz of z squared equals to 2z. No surprises there, right? So just to recap, the theorem of caratheodory is incredibly useful because it allows us to characterize complex differentiability by an equation which is an identity for the function. That equation, notice, this right here is really the key idea, that we can write f of z equals to f of a plus phi f of z times z minus a. That understanding that that is what complex differentiability tells us about the function, that we can write the derivative, we can write the formula for the function in that way. That is incredibly useful for theoretical questions. Like one of the questions in your homework, I ask you to prove that if the function is complex differentiable, then it's continuous at the point. All right? If you start with what I boxed in red over there, that is like an incredibly easy homework problem. If I say anything more, I will solve the homework problem. Like it's that easy. Okay, so. Yep.
So could you also let phi of z be minus a?
Nope. No can do. I have to factor out z minus a.
Oh.
So, yeah. I think. Yeah. I was going to say, I think, yeah, number 2 in the theorem, exactly. I just erased it. That pattern is not up for grabs. It's got to have that z minus a there. So like, again, if you read the notes, I have like 3 more examples. I'll let you guys look at those. They have weirder calculations in them. But essentially the point is to start with f of z minus f of a, and then do algebra such that you factor out z minus a, however it takes, by hook or crook or whatever. I think in your homework I gave you z cubed. That's not much harder than this. You just have to factor out, how do you factor z cubed minus a cubed?
Difference of 2 cubes.
Difference of 2 cubes, right? So that has a z minus a factor, so whatever's left must be phi of z, the difference quotient function. Let's try our hand at something a little bit more troublesome. Example 5. What? And I don't know how this is going to go. Like, this is new to me, guys. I haven't tried this yet. E to the z. What happens if I look at, f of z minus f of a for this thing? What do I get? I get e to the z minus e to the a, right? And I guess I can just rewrite that as e to the z minus e to the a over z minus a times z minus a. I mean, I can do that, right? So apparently this would be the difference quotient function for this one. And how do you calculate the limit as z goes to a of that? Anyway, this is just a fancy way of me asking the same question. What about complex differentiability of the exponential? Can you hack the limit of that quotient? And so in the notes, I look at it in real notation. It doesn't make it any better. Okay? Like if you put it in terms of sines and cosines and exponentials, it doesn't get any better. It is a genuinely, as all derivatives are, right? All derivatives have type 0 over 0. They're indeterminate form. That's what makes it so interesting. That's what's the difference between Newton and its predecessors. This is something that defies just algebra, the derivative. So we can't make any progress on that with our current technology. We need a new technology. All right, so what's next? Cauchy Riemann equations. All right. And so here's the theorem. If f equals to u plus iv is continuously differentiable at, let's say, z naught, then, u sub x is equal to v sub y, and well, u sub y is equal to minus v sub x, then f prime of z naught is equal to ux plus I vx at z naught. In other words, if you have a function which is continuously differentiable at a point and satisfies the Cauchy Riemann equations, it's complex differentiable. What is not present in this theorem that has been present in my previous two? The thing that Shane wanted to put on me. The limit. There's no limit here, right? Well, the limit's hidden in the continuous differentiability, right? But it's not in your face, is it? So let's try the exponential in this way. I'm going to prove the theorem next, but check it out, right? So f of z is equal to, e to the z, which is what? E to the x cosine y plus I e to the x sine y, yeah? That's your friendly neighborhood complex exponential. Here's the real component, u. Here's the imaginary component, v. So you guys tell me, what's u sub x? Well, before that, are these continuously differentiable? Can you take partial derivatives of these, and are those partial derivative functions themselves continuous? The answer is yes, forever and ever, amen. These are smooth, right? You can take as many derivatives as you want. It's endless. So yeah. And so what we got here is ux is equal to e to the x cos y, and uy is minus e to the x sine y. Vx is e to the x sine y, and vy is e to the x cos y, right? So I just did the partial derivatives, but check it out, right? So Vx is in fact equal to, well, however you want to do it. This is equal to what? I can't fit it in here decently. Let me do it over here. So as you can see, Vx is what? Minus uy, right? And here Vy is equal to ux, right? There's another theorem which is true, which is that if the function is real differentiable, let's say here, if the function is complex differentiable at z naught, then, well, hold on a second. Let me not say it wrong. Oh, so so the Cauchy Riemann equations hold, right? So by the theorem, what do we have? What's the derivative of the complex exponential? I said it was ux plus I vx, right? According to the theorem, which is what here? Ux was e to the x cos y plus I what? E to the x sine y, also known as what? E to the z. So the derivative of the complex exponential function with respect to a complex variable is the complex exponential function once more. My wife was telling me about some post she saw on Facebook. It's some lady thinking about, it's like a meme. She's thinking about her future husband, and she's like, I'm going to change him. And like her picture is like DDZ. And like a picture of her husband is like e to the z. It's like, so it happens to coincide with class today. That's just an example of God's providence right there. So, although I think I adapted it to complex, it was x in the Facebook post, because real calculus has a much wider audience. Although my wife was the only one who laughed at the joke, and then the person had to explain it to the rest of his friends. So, still. But that's the difference between the power of one and the power of many, I suppose. All right, where was I? Probably running out of time, if I had to guess. Get in there. All right, so theorem 5.32, I say if f is complex differentiable at z0, then f is real differentiable at z0 in the Frechet sense, and blah, 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 blah. Yeah. So theorem 5.32 is not this theorem. This theorem's actually, this is theorem 5.34. So I started with the more interesting one, all right? Theorem, like I said, theorem 5.32 says that if you have a function which is complex differentiable, then it's real differentiable, and its partial derivatives have to satisfy the Cauchy Riemann equations. That's a different statement than this, right? This I start with real data, continuously differentiable, that's in the real sense. We satisfy these equations between the real partial derivatives, and from that we conclude that the complex derivative exists. So a kind of converse type theorem is sort of this. If f equals to u plus iv, and f prime of z0 exists, then f is real differentiable in the Frechet sense, okay? At z0, and ux is equal to vy, and u sub y is equal to minus vx at z0. Moreover, the Jacobian of f, right, which has the form what? Partial f, partial x, partial f, partial y. So what does that look like? I mean, let me write it out. This is ux, vx, uy, vy, right? So what I'm claiming here in this theorem 5.32, I think it is, that the Jacobian of f, has the Jacobian of f is actually equal to the matrix representation of partial f, partial x, where this is that standard representation of the complex numbers we talked about last time. Actually, I shouldn't say that here. My bad, guys. I should say kind of more, it's not wrong what I said, but this is better. It is the matrix representation of the derivative. And if you remember last class, that was equal to f prime of z0, and then I f prime of z0 for the next one, right? So if you put that all together, what does that tell you about the x and y derivatives? So apparently what? F prime of z0 is equal to what? Partial f, partial x, right? And partial f, partial y is what? Apparently it's equal to I times f prime of z0. So a good part of this theorem 5.32 is really just rehashing what we talked about last class in terms of the relation between a 2x2 matrix being the representation of a complex multiplication and what that means for the derivatives. Like if that's the case here, then the x and y partial derivatives have to be related in this way. All right. So I haven't proved either of these theorems. I think I'm going to use the projector here to look at the proofs of the theorems, if that's okay with you guys. So let's do that. Uh-huh.
Why are we using A again for the...
Oh, instead of Z naught?
Yeah.
No reason, really. Just to not write Z naught 20 times, mostly. A is easier to write. And I mean, so if I could do everything over again, maybe I'd go back to the very start and put A instead of Z naught. We do like the limit as x goes to A of f of x minus f of A over x minus A in Calc 1. So that's more or less where that's coming from. If that.
If we, I mean, not that you would mix it up all in one problem, but you could kind of just use it interchangeably.
Yeah, I think the real issue is you can't use Z, and like you can't do the limit as Z goes to Z of f of Z minus f of Z over Z minus Z. Like that's not allowed. That's not going to work. We do need to distinguish between like the point we're trying to find the derivative at, and it's the same thing as calculus 1. Like, do you want to do the limit as x goes to A, or do you want to do the limit as h goes to 0? It's that whole discussion again. And sometimes I find it convenient in Calc 1 to talk about x naught rather than A, just because it's still an x. So it's making the reader think this is an x value. Whereas A is just, well, A gets lost in sentences sometimes, right? Like, for some reason. Yeah. So nothing terribly exciting. Oh, Shane, I was noticing that if you're interested in the proof of uniform continuity, it implies continuity for a sequence. I think it's given on page 106 of the notes in here. Yeah, because I do talk about that stuff eventually, but I might not talk about it in here this semester. Hey. So because I figure you're getting it in the other class, and although if the other students said that they really, really want to see that, I could be talked into it. Sprano over there? Sorry, we're way in the future. The future. All right, come on, come on. Let's get back past the Vertinger calculus. Ooh, Cauchy Riemann and polar coordinates. I don't always cover that, actually. Let's see here. So, finally back to the theorem. So suppose we have a complex differentiable function at a point, all right? And I would like to prove that implies it's real differentiable at the point, okay? And not just that, but that the real partial derivatives satisfy those conditions that I just said. And the proof goes like this. So if I have a complex differentiable, like I just told you guys, like is theoretically so nice to use the theorem of caratheodory. There you go. This has all of the information about it being complex differentiable. It is equal to f of z naught plus f a phi of z times z minus z naught. Look, I'm back to z naught again. Yeah. Now, if I swap this out for like z plus h rather than, if I let, so this is like a substitution, right? So this would imply that f of z plus h minus f of z naught is, phi of z naught plus h times h in the other notation. All right, so with that substitution made, I'm going to claim that the real differential, the Frechet differential, is exactly given by the complex multiplication of the derivative times the input. That's a claim. All right, and to show that, I need two things. I need that that's a, I'm trying to prove real differentiability, right? So there are two things I need. I need to have that it's linear in the real sense, right? And I need to have that it is satisfying the Frechet quotient. Linear in the real sense is just kind of like a duh. Like if I put in h plus h1 plus h2 here, it puts h1 plus h2 here, and then we just use like distribution of complex numbers. So like linearity of this formula is just manifest. All right, it's just clear. The difference quotient goes like this. So I